Hello and welcome everybody to our contribution to the Battle Team 2020, the battle of the leakage detection and isolation methods. My name is David Steffelbauer and I'm a Marie Curie Fellow at the Water Management Department at TU Delft. This work is a joint effort between me, Jochen Teuerlein from FreeS Consult from Karlsruhe, Denis Gilbert and Olivier Biller from INRE, Bordeaux in France, and Ido Abraham also from TU Delft. The five of us together built the team under pressure. To solve the leakage problem of the L-Town water utility, we have proposed a hierarchical approach to find the leaks in the three measurement zones. This presentation follows exactly this approach. First, we will start with the calibration of the network, both for demand and for roughness. Then I will introduce the foundation of our work, the dual model approach, which makes finding leaks tremendously easier. Last but not least, I will give an overview of our methods to detect and to localize leaks, which are both based on the dual modeling approach. Let us start with the demand calibration. We focused on the AMRs in measurement zone C of the network and used time series analysis to identify the water usage behavior in L-Town. The idea is to subsequently infer the demand to unmeasured nodes in zone A and B according to the information from the previous water bills, which is contained in the EPANet input file. The zone contains residential, commercial, and industrial consumers. We used time series analysis to derive general demand patterns for the commercial and the residential consumers. The best model for both user groups has been a multiplicative time series model consisting of a trend, T, a weekly seasonality, S, and a random noise component, R. At the bottom of this slide you can see on the left side the trend over the year for the residential and the commercial users, and on the right side the seasonal component that repeats every week. It has to be noted that the industrial users follow the same model, although with different seasonal periods, which repeat with prime numbers all 7, 11 or 13 days. Since there are no industrial users in zone A and B, we were only interested in residential and commercial demand patterns. We stated the roughness calibration as a weighted least squares problem with bound constraints, which was solved with the help of Levenberg-Markov algorithm. We grouped the pipes into 6 groups, one belonging to measurement zone B, one to C, and the remaining 4 groups were divided according to their diameters and original Hazen-Williams coefficients, according to the EPANet input file. On the right side of this slide you can see the convergence of the roughness parameters. Additionally, our method allows to compute confidence intervals for the roughness parameters based on first-order second moments. All groups resulted in very certain and reasonable roughness values. Group 1 and 5 show bigger confidence intervals due to their small number of pipes and the fact that they are hydraulically not that influential in the system. Now we get to the core of our idea to detect and isolate leaks, the dual model. In the dual model, the original pressure measurement nodes are connected by a valve with the virtual reservoirs. The origin of the name dual stems from the fact that instead of using a fixed demand boundary condition, the dual fixed heads are used. The heads of the reservoirs are set equal to the pressure measurements. If a new leak appears in the system, the residuals between measured and calculated pressures are increasing. The pressure drop caused by higher flow velocities towards the leak in a real system is not observed in the model that is still based on the leak-free system. In the dual approach, the measured pressure drop is applied to the fixed head reservoirs, and as a consequence, an additional outflow is calculated. This outflow can be understood as outflow residual. The advantage of the dual method is that the calculated outflows act as an amplifiers that deliver significant and localized signals even for small pressure drops. In addition, the outflows at the virtual reservoirs are a good first estimate for the leak size and location, as you can see on the right side. For the leak detection, we make use of the dual model outputs, the virtual leak flows. As mentioned before, the leak signals are amplified by the dual model, whereas the noise levels are way smaller than using the original pressure and flow measurements. The virtual leak flows show 2 different types of leaks that occurred in the system: instant leaks and growing leaks that saturate at a certain level, both shown on the left side. For the growing leaks, the increase over time was modeled with a quadratic function. We used change point detection algorithms like CUSUM and the likelihood ratio method to retrieve first estimates for the leak start times. The input parameters of the algorithms were calibrated on the small noise levels that were still remaining in the virtual leak flows. To retrieve even better start time estimates for the battle, we made use of Bayesian inference for single occurring leaks, which used all flow and pressure measurement signals as input parameters to fit the identified leak shapes on the measured signals. With this method, we were able not only to retrieve confidence boundaries for the start times, but also simultaneously probabilities for the leak size as well as the pressure drops in the system. If multiple leaks occurred at the same time in the system, this method had difficulties to find the right parameters. That is why we fell back on a simple genetic algorithm in the case of simultaneous leaks. The virtual leak flows from the dual model were also used for finding leaks. The localization is based on the work of Perez et al., which used Pearson correlation coefficients between pressure residuals and sensitivity matrices. The difference in our method is that we are not using pressure residuals, but instead the residuals in the virtual leak flows, which makes the method way more stable and robust. On the right side you can see the fitness function values based on the correlations. The smaller the values, the lighter the colors of the pipes, the more likely a pipe is to be the actual leaky pipe. The last slide shows the results that we obtained with our method. In total we have found 32 leaks, or in other words 22 leaks additionally to the 10 leaks that were already identified by the L-Town water utility. On the right side you can see the locations of the leaks, on the left side when they happened in the system. 4 leaks were identified in Zone C, 2 in Zone B, and the remaining 26 leaks occurred in Zone A. The leak sizes vary between 1.33 and almost 10 liters per second. In total, the L-Town water utility has lost 665,000 cubic meters of water due to leaks in their system in the years 2018 and 2019. So, that was our short presentation, and I want to thank you all for your attention. If you have any questions, I'm happy to answer them via mail, or we can also meet virtually on Skype or Zoom.